Hey everybody, going to start part 2, actually part 9 of this 3D modeling with AR series. We're going to take the same cone that we made in part 8, from an Algebra 1 geometry perspective, taking a linear function, spinning it about the x-axis, right, to create a cone. But right here, we're going to look at it more from an approach of more of a pre-calculus, even calculus, multivariable kind of way of actually modeling this right here. Algebra 2 pre-calc kind of a level here, all right? So we're going to take this cone here, radius of 3 3/10, height of 9 8/10. We're going to actually build this right on our tablet, okay? And we'll try to do it in augmented reality. But we're going to do it through a means not of taking a linear function and spinning it. We're not going to revolve anything this time. Here, we're going to work with the parent cone function, right? Just like the parent linear function in Algebra 1, f of x equals x. Quadratic, f of x equals x squared, right? Cubic, x cubed. Absolute value function, absolute x of v, right? Well, there is also a parent cone function here. And anybody know what it is off the top of your head? It's okay if you don't. And again, most of your students won't know it either, but let them Google it. Let them look it up. It's analyze why. We'll do it right here and right now. So I'm going to share my screen here. We're going to rock and roll. All right, fractal. Let's get rid of that. And so what I'm going to do, we have right here, get that picture from last time, right? I have my tablet here, my iPad projected up here onto my screen. All right, and so there it is. All right, so I'm going to go into the 3D calculator now. There it is. All right, and so now the parent cone function actually has the equation, the square root of x squared of the quantity x squared plus y squared. Looks like that. All right, kind of see how it's kind of like a piece of paper kind of opening up whichever way, whatever, right that. But now I might change the color to a little bit. I'm kind of partial to the blue, but I don't know. What do you want? We'll make it... yeah, we'll make it some kind of nice turquoisey blue there. All right, but here's the thing though. I could take this cone, right? I could throw it in my environment here. Excuse me. Let's get some light here. Boom, I love that square. Oh, I love the clarity here. It's amazing. So you take that, we'll go right here. It doesn't even look like a cone sometimes. Oh, but it is. Now we look at it, and so now the thing is that a good model here? And you're like, no way, no way. But see here, now we have to transform this surface function. Yes, we have two variables, and in this case, z, the height, the distance above or below that horizontal coordinate plane that we're so used to working with in Algebra 1, right? That z is a function of both x and y. No matter what point you are in the coordinate plane, you can this function determines how high up you are. But let's just talk about first things first. Look at this thing. My cone doesn't look like this, does it? No, it looks like this. And so I work with students. So like, well, what do you got to do? And most people tell me, oh, just put a negative, flip it upside down. You see, oh, but wait a minute, where did it go? It disappeared. Aha, here it is. If I go to the tools section, hit more. All right, GeoGebra defaults, AR defaults are showing now above the coordinate plane. But if you scroll down a bit and hit the Move Graphics View tool, you can actually take that, touch it, and see I can actually slide that up, and whoa, it's like forming. It's kind of freaky, but it's pretty cool, right? You got that thing going on right there. So, I mean, I can go back to 3D just to work with it more. I mean, it'll be there in 3D, of course. Always will be there in 3D, but I forgot about that. But I'm glad I got to show you right here. But you look at it and say, Tim, it looks good, but we have to sort of trim that thing off, because that, especially people who where neatness is a big quality, and it should be right here. You know what, that it chops it off here, but when I saw it before, it kind of like if I actually go back and move it up a little bit more, well, this way, see how it looks like? It looks neat. I gotta sort of skim it off a little bit, don't I? And the answer is yes, we do. But let's go back to 3D and do it. The question is, how do we? We gotta kind of like just take a horizontal. It's almost like you're gonna move that gray plane down a bit and then just take the part above it, right? But I'll tell you, the cone here had a radius of 3 3/10. All right, let me actually just get my camera here rolling so you can see it better next to my. Actually, that won't work. I don't have the screen there, but this thing has a radius of 3 3/10, a height of 9.8. Remember, jot it down if you have to, because I want to keep going back and forth. All right, 3 3/10 of a radius. So now in Algebra 1, we talk about restricting the domain of a function where, y is a function of x. But in this case here, z is a function of x and y. So if I were to just put x squared plus y squared less than or equal to, what was the radius again? 3.3 squared. You see what I mean? In this case right here, notice how interesting that looks like. It actually trimmed it off. the radius of that bottommost circle you see right there is actually 3 3/10. See, it's like, see, I mean, most people would tell me, hey, this what you're scrolling through right here, Tim. This is an equation of a circle in the coordinate plane, and you're absolutely right. So, and for any point inside that circle, those are points on the cone that are being plotted there, if you will. All right. But now, the height of this cone is 9 8/10. Is it not? So, oh yeah, it is. So let me actually go back and let's move this down because we're going to actually bump this guy up a little bit. Move graphics view. So see, I can move graphics view. Let's you go up and down, up and down. I'm going to have to show enough there. But that cone had a height of what? 9 8/10. Let's go back here. And so let's just say, for example, let's just for the heck of it, put plus 9 8/10. What is it going to do? Oh my gosh, Tim, it shifts it upward. And yes, you're absolutely right. But we don't see all of it because it's truncated a little bit because of our view. So move graphics view right at the bottom. And we shift, let's move it down here. Hang on a second. Why is it doing it? There we go. Patience. Perfect. Right? But there's a big problem now, isn't there? Because move graphics, let me go left and right here. Let's see, right there. Seems like the problem becomes like, well, that's great, Tim, but your cone is like levitating in midair. It's not like touching the ground, is it not? And you're absolutely right. Let's just see. Let's see that from so we can see the dimensions too. Look at this. It's off the plane, definitely, right? But the problem is that it's not touching the floor. I mean, this is 9 8/10 above the ground, right? And that radius there is 3.3. But something has to change here. Something's got to give, and you're absolutely right. And it happens to be, sorry, it happens to be our ratio here of. Let me just undo what I did because there we go. I accidentally had the move tool on, the move graphics tool on. I shouldn't have, but this is what I wanted, right? Get this mouse out of the way. So right here, like notice here, this looks pretty good, right? But that's still far from a perfect model. You would agree. So it's almost like something's got to give here. I mean, if we talk about slope in Algebra 1, right, isn't this, we talk about the change in y over change in x, but in this case, let's look at delta z here. The change in z, it's 9 8/10 divided by, well, shoot, I just said it, divided by what? 3 3/10. So if we go back here, right, we could think of slope in 3 space, even though that word is meaningless because there's infinitely many directions. You could talk about we call that, directional derivative, all that stuff. That's like calculus 3 terminology. But if we only look at just x and y, our Algebra 2 pre-calc and calc students can totally do that. We can look here and say, you know what? What if we were to actually just put like a scale factor in front of here? We got to stretch this thing vertically to make it hit the floor. Well, what's that scale factor going to be? I would have kids guess and check, but to save time in the video, isn't it really the ratio of the height to the radius? Negative 9 8/10 divided by 3 3/10, and enter, voila. There you go. So let's see if the logic here makes sense. 9.8 to 3.3. That's the delta z to delta x ratio. It also happens to be the delta z to delta y ratio right there, right? Totally is. Again, we're talking about how z changes with respect to each variable. Pre-calculus kids can do it. They really can. And also the bottom radius of, 3 3/10 there. So now let's put it to the test. This is the moment we've been waiting for, right? The icing on the cake, baby. Let's get rid of all this. Let's see how well our model fits. Granted, I know it's not a perfect model because I cut this out just like little sunspots, but for the most part, to me it's not bad. I'm gonna actually order one of those model sets there, that they sell those districts and stuff in those catalogs. But I did this once at a high school. Every high school I go to, I actually ask teachers to get me one of those sets with cones and spheres and stuff. And we'll actually build the model cone they have there. And I'm telling you, the ones that are built out of plastic versus this cardstock, the ones that are built out of plastic like map on perfectly. They latch on. And when I walk away from it like this, this cone is glued to the floor itself. Like literally, you can go inside of it too. I mean, you could spin around, do a 360. You can do whatever you want. This is so much fun. Now, your kids can model in this environment all the time. And so why not give them, the opportunity to do so like that? So that's another way you can have kids modeling in GeoGebra 3D with augmented reality. Again, in this case, not so much through a surface of revolution logic, but we'll talk about an actual function transformation logic. Remember, we built the absolute value function using equilateral triangles, and we translated those by the vector, the height of the prism. But we also, in another screencast in this series, we also did an absolute value surface function. Z equals absolute x. Oh, z equals negative absolute x, because you flip it upside down, and then we add the scale, the delta z to delta x appropriately. Okay, concepts students learn, in 2D can totally analogously be applied in 3D. And if they can model in 3D, all those standardized non-authentic tests that only ask in 2D, not going to worry about it. Okay. That is the power here of GeoGebra 3D with augmented reality. So if you like what you see, feel free to subscribe. Got more coming in the series. So thanks for watching. Have a great day.